In general, we'll kind of have two different types of these optimization problems. One type is the business application dealing with profit or revenue. The other type is about geometric shapes or problems involving geometric formulas. This is one of those types of problems. The same steps apply though, so the first step, get organized, pause the video and read the problem carefully. Next, let's identify the objective. In the problem, they're talking about making the enclosure as large as possible and finding the max area. So in this problem, our objective is to maximize area. In these geometric type problems, it's really important to sketch a diagram or some sort of picture to better visualize what we're building. So the farmer is building a rectangular enclosure along a straight wall. I went ahead and drew in the straight wall. The side along this wall doesn't need any fence. So let's go ahead and draw out the enclosure. It's going to be a rectangle, so it'll look something like this. And again, that back piece against the wall doesn't need its own fence piece. The objective is to maximize the area, so we want to make this area inside the enclosure as large as possible. Let's move on to step 2. We want to create the function that we're going to optimize. Since we're maximizing area, we will create an area function. Let's just first though think about, in words, what area is equal to. Recall from geometry or a high school algebra class, area is equal to length times width. So I'll create an area function based on those two components, length and width. Looking back at my picture though, I don't know what the length and the width are. When something is unknown in a problem, that's our key that those things will be our variables. So I don't know what the length is going to be. So I'll measure that with an unknown or a variable. Let it be x. I don't know what the width is going to be either. So I'll label that with a variable, y. Since this is a rectangle, the width here on this side and this side will be the same. So this one will also be y units long. Now, based on those variables I have in place, my area function, again, length times width, but let's just fill it in with the appropriate variables, x times y. So technically, we have created a function to optimize. It's an area function, but we have two problems. The first problem is that this function has two different variables in it. And at this point, we don't know how to take derivatives of two different variables. It's called multivariate calculus. So I need to get my function all in terms of one variable. The other problem is that we're missing some vital information. Up in the problem, it states the farmer has 1,000 feet of fence. So that is a constraint that the farmer has. And our function doesn't include that vital piece of information. So we have to include that somehow. So let's think about this constraint. The farmer only has 1,000 feet of fence to put up these three pieces for the enclosure. Those three pieces, if we're thinking about putting them together to build this, would be the x piece, the length, plus the two y sides must equal 1,000. Now my job is to include this information about the constraint into my area function. The way I do that is I solve my constraint equation for one variable. It can be either x or y, but in this case, x is going to be much easier. So I subtracted 2y to both sides. Now let's go back to our area function and plug this in for x. So my area function was x times y, but instead of x, I will write 1,000 minus 2y, because that's what x equals, times y. So now I've solved both problems at the same time. My area function is now in terms of one variable, y, and it includes the information about that constraint that the farmer only has 1,000 feet of fence. Before we move on to step 3, let's go ahead and distribute the y to both terms. Alright, we are ready to move on to step 3. Find the critical numbers, take the derivative, set it equal to 0, and solve for x. So the derivative of my area function is that, set it equal to 0, and solve for the y value, in this case, the variable that makes it true. I'll let you do the algebra on your own, but we'll find that y equals 250. Going back up to our picture, I know that y equals 2. So the sides here are 250 feet long. I just need to figure out what the length is. Along the way, we created this function for what x is equal to. X is equal to 1000 minus 2y. So let's plug our y value into this function to find the x value. Minus 2 times 250 is going to give us an x value of 500. And there's my missing third dimension. X, or the length of this enclosure, is going to be 500 feet. So there we've found the dimensions that make the enclosure as large as possible. The last thing we need to do is find the maximum area. So here we're in step 4. We're using these critical numbers to answer the question parts. To find the maximum area, we just take the length times the width and multiply them together. So 500 times 250 for a total area of 125,000 feet squared. So the area of the space in here is 125,000 feet squared. And that's it.